Hello everyone, welcome to my programming club. Today we will be solving the problems of weekly contest 361. Now let's move to the first problem of the contest, and the problem's name is count symmetric integers. So you are given two positive integers low and high. An integer x is considered symmetric if it consists of 2 into n digits, and the sum of the first half of the n digits, first n digits is equal to the sum of last n digits. So this kind of number is said to be a symmetric number. You have to return the number of symmetric integers in the range low and high, both of low and high included in the range. So let's have a look at the constants. So constants are these low and high are of order 10 raised to power 4. So how we will be solving this problem? So if we let's say the maximum size is 10 raised to power 4. So at max 5 digits we have to check. So for each number in the range low to high, uh, we will be iterating for each number. Each number in range, and we will check whether this is a what was the name of the symmetric number. Check if it's a symmetric number. Symmetric number. So let's have a look at the approach. Firstly, you will count the number of digits in the number. Then you will, if you know how many number of digits are in the number, then you will divide the number of digits by 2. Let's say the number of digits was capital D, or say size of your number was capital D. These are the number of digits. So you will add D by 2 digits to a variable, and D by 2 digits to another variable, and check if sum of D by 2 digits and is equal to other D by 2 digits. So it is essentially nothing but sum of first n numbers n digits being equal to sum of last n digits. So since it is a 5-digit number, so length at max will be 5. So to check the length, your number of digits, your loop will be running at max 5 times. Then once you are done checking with the length of the digits, then you will run a loop to get this sum. This will also run at max 5 times. So this overall solution will be pretty much of linear time complexity, and so your solution will be accepted since 10 raised to power 4 is lesser than 10 raised to power 8. So these are the number of operations of your program. The solution, and this is the limit of number of operations in 1 second. So if the number of operations of your solution happens to be lesser than this limit, then you will get a accepted solution. And if the number of operations in your solution becomes equal to this limit or exceeds this limit, then you may get a TLE. But here, since it is lesser than that, so our solution will be accepted. Now let's have a look how we are approaching the solution. So first of all, the number of digits in a number should be even. Only then we will be able to divide the uh, digits in the number in n and n parts. So it should be a even. So we will count the digit of the number. This is the function to count the digits. And only those numbers will be considered whose number of digits are even. Once you know the number of digits, you will find the sum. So sum will return two things, sum of the first half and sum of the second half. Half, sum of second half. The logic here is pretty much straightforward. We are checking what is the length of what is the count of the digits. And then for half part of the number of digits, we are adding it to one variable, sum 1. And for the last n digits, we are adding to sum 2, and then we are returning this pair. And if the sum of first half and second half becomes equal, then we will increment our count, and at last we will return our count. As you see, the solution is getting accepted. So that's the first problem. Now let's move to the second problem. So the second problem's name is minimum operations to make a special number. So you are given a string which is representing a number. String is zero indexed, and in one operation you can pick any digit of the number and delete it. If you delete all the digits of the numbers become empty, and it will become equal to 0. So the minimum number of operations required to make the number a special. So a number is considered special if it is divisible by 25. Let's check what is divisibility rule of 25. 25. Divisibility rule of 25 says that the last two digits of a number, either zeros or a number that is divisible by 25. So for a number to be divisible by 25, we will check for if the last two digits are 0 or it's 50. These are the two digit numbers that are divisible by 25 or 75, or let's say it's 25. If any of these satisfies, then the number is divisible by 25. Otherwise, it's not. Then what you have to do is, let's say the number was giving something like this. Let's say a big number is given 3, 4, 5, 6, 7, 8, and then 5, 8, 9, 7, 0. So you have to tell what is the minimum number of deletions you have to make it divisible by 25. minimum number of deletions. So we will check for the occurrences of these 50, 75 or 25 one by one. Firstly, we will check for 0, 0, 0. Now it need the 0, 0 string. We will match the string with this. We will match this pattern with this string. This pattern can be present in not contiguous manner. It can be present in a non-contiguous manner also. For example, 50 is present like this. 5 and 0 are not together, but they are separated. So once we know what is the index of the, let's call this the zeroth index, and this is the first index. Now, as soon as you know the what is the index of this zeroth index in this particular string, let's mark the indices 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now you know that 50 is completely occurring at 6, and in total there are 10 indices. So 6 minus 10 will be 4. But 50 is also having one digit of another digit which is 0. So we will subtract 1, which will be 3. So 3 deletions are required. These numbers should be deleted. The minimum these we will be considering minimum of these options, checking for each of the pattern, and then we will accordingly answer. So this is the solution. So more will be clear in the coding part. Now let's quickly move towards the coding part. As you can see, we are checking for 0, 0, 25, 50 and 75. Whichever of these patterns gives us the minimum number of operations, we will consider that pattern. Well, a thing to be noted here is, suppose none of these patterns exist. 1, 2, 3, 4, 5, 6, 7. So none of these patterns exist. 0, 0, 25, 75, 50. Let's say there was some 0 here. So none of them exist. So the number will not be divisible. Only number that would be divisible will be 0, since 0 is divisible by every number. So we will check if this particular string is having any 0. Then let's say the length of the string was 0, 1, 2, 3, 4, 5, 6, 7. So the length is 8. String is 8. Since it's true that the number is having 0, so it will be 8 minus 1. 7 deletions will be required. 2 here and another 5 here. So I hope you are able to understand. If would have, if let's say it is a case that 0 is not here, and let's say the length is 7 now, so 7 out of 7 numbers should be deleted, and once the string becomes empty, it will become equal to 0, and 0 is divisible by 25. So that's the case. So let's have a look at the solution. So firstly, we will check if 0 exists. This is to check if 0 exists in the solution. We will check if 0 exists in the string. To take care of the case when the number is not divisible, is not having any of the patterns we are checking for. which are, or say that is 0, 0, 25, 750, 75. None of these are present in the given string. Then we will check if 0 exists. So we will be using a pointer index. It will be starting from, we are checking the string from the very end in this direction, right to left. So a pointer will be pointing towards this position. Initially it is called index. Index will be moving in this fashion. So it's initially pointing to size of string -1. This is the last 2-digit pattern that we will be matching. So firstly we will match for the last digit, which is this digit, this one. In 25 it will be 5. Firstly we will be checking for this digit. Then once we are done, if we did not found the last digit, then we will check if 0 exists. Then we will reduce the size of the string. The number of deletions will be reduced by 1. Otherwise, whole string should be deleted. Now, if that's not the case, this is when the, or let me change the theme. I think it would be fine to differentiate between comments. This is when the string is not having last 2-digit patterns. So if that's not the case, we will match the first digit. So once we are done matching the first digit, we will return this number of indices, the position of the first digit in the given string of these two last digits, S1 for the last digit to be excluded. It's mentioned here also. So that's pretty much it. Now let's try to submit it. As you see, the solution is getting accepted. So let's move towards the third problem of the contest. So the name of the third problem is count of interesting subarrays. So you are given a 0 indexed array nums and an integer modulo and an integer k. So your task is to find the count of subarrays that are interesting. Subarray is a non-contiguous, non-empty sequence of elements within an array. For example, one, two, three, four, five. Non-contiguous, non-empty part of the original array. So this can be a subarray. Now this whole array can also be a subarray. Basically any part which is contiguous and non-empty. So it cannot be like 3, 5. 4 is not present, so it's not contiguous. So this cannot be a subarray. So I hope it's clear to you what a subarray is. So you have to return the number of operations. I read this is the problem. So you have to return such subarrays in which the count of the integers which satisfies this condition nums of I, count is the number of the indices such that the number on that indices modulo is equal to k, and also the count of such indices is equal to k. So what the problem statement is saying, let's take an example. Let's take this example. Let's say we consider these subarrays. First, the subarray considered is 0, 0, which is 3. Now, 3 modulo 2 equal to 1, which satisfies this condition. Hence, the count is 1 for this particular subarray. For the subarray or between the indices 0 and 0, count is 1. And count modulo is equal to k. So this also satisfies. This is one subarray that is interesting. So another subarray that we will be considering is 3, 2. This is the only, there is a only index I is equal to 1 in the range 0 to 1 that satisfies this modulo condition, and count is 1, and count modulo is equal to k. So similarly, we can take the whole array, and there is only one number, which is 3, which satisfies this condition, and so the count of such number is 1 here. So 1 modulo 2 will be 1, which is equal to k. So overall, 3 such subarrays exist. So we will return 3. So how we will be solving this problem? First of all, I would like to introduce you to a concept. If you already knew it, then very well. If not, then you should. It's called prefix sum plus hashing. What I mean by this is, uh, let's say target sum is given to be x, and let's say there were some numbers which were summing up to, let's say, x, and then there were again some numbers. There was something like this. With this. Now, if you do prefix sum, when you will be here, it will be x plus 4. So if you keep storing this, or let me quickly move towards the coding part, there you will be able to understand it in a much clearer way. Basically, what we will do is, first of all, for all the numbers, either they satisfy this condition, number modulo equals to k, or they do not satisfy this condition. All of the numbers in the array that are satisfying this condition will be contributing 1 to the count, and all of those which are not satisfying the condition they will be contributing 0. So all of the array will be turned into a set of 0 and 1s. You will be using a variable prefix sum. Prefix sum is nothing but as you are traversing this whole array of contributions from left to right, you will be keeping adding these values to the prefix sum. So here prefix sum will be 1, here it will be 1, here it will be 2, 2, 3, 3, 4. So these are the values of prefix sum. So essentially what you will do is whenever you are adding a new number contribution to the prefix sum, uh, this is firstly what you will do is, let me quickly change the theme. First of all, you will convert the given nums array elements into their contributions to the count. So then you will be taking a value variable prefix sum. This prefix sum variable along with hashing will be used to check whether particular some particular subarray with a given sum exists or not. You will be adding each new value to the prefix sum. Then you will be subtracting prefix sum minus k, and you will be checking. Uh, let's say we take this example. You are checking for this target. What you will do is, this is your prefix sum. You will minus target from it, and you will check how many times. Let's call this sum. How many times this sum is some have been quoted before this point. It will add to number of interesting subarrays. You can take an example and try to dry run it. So you will check for the number of times previous sum has been quoted before this value of prefix sum, and that number of times will be increase in the number of interesting subarrays. So at last you will be incrementing the difference of prefix sum. You will increment the this particular value of prefix sum. So at last you will be returning your result, which is nothing but this result is nothing but number of interesting subarrays. So let's try to submit it. As you can see, it's getting accepted. So let's move towards the final problem. So before moving to the solution of this problem, let's firstly we have to read the problem obviously. So the problem's name is minimum edge weight equilibrium in a tree. Basically, let me describe this problem in my own words. So what you are given is you are given an undirected tree. Undirected means that the edges are not having any particular directions. So let's say there is an edge between U and V. This is U and V. So you can go either from U to V, this direction, or you can go this direction. Since the edges are not directed. So this is the meaning of undirected. And tree is a graph which does not have any cycles. So it cannot be like something like this. So this is kind of a graph which does not have cycle or self loops. So a tree is given to you and the nodes in the tree are labeled from 0 to n minus 1. Total there are n nodes. Then a array is given to you called edges, which is of the form u, v, and w. There is a edge between node u and v, which is having weight w. So these two are the nodes. This is the edge weight. So this is what you are given. And then let's say a tree is given something like this. And this is u, and this is v. And this is the root, suppose. So let's consider the weights x1, x2, x3, x2, x4. So you have to tell what is minimum number iterations operation here is change weight of a edge of an edge between two nodes. Tell with what is the minimum number of operations required in order to make the edges between the path from U to V, or say V to U, of same weight. So if the edges are having weight something like this, how many number of operations are need to be carried out on this particular path that all of the weights are having same value. So at most two operations are needed, since x2 is having frequency 2, x3 is having frequency 1, x4 is having frequency 1. So these two are required to be changed into x2. So minimum two operations. And this question will be asked you for, let's say, q number of times, or say q queries. U and V will be given to you, and you have to tell what is the minimum number of operations required in order to make all weights between U and V equal. So this is what you have to tell. So you can read in the problem statement also. There is an undirected tree with n nodes labeled from 0 to n minus 1. You are given an integer n and a 2D integer array edges, which is of the form U, V, and W, which indicates there is a edge between the nodes U and V, which is of weight W. Weight W is the weight of the edge. You are also given a 2D integer array queries of length m, where queries are of the form A and B. For each query, you have to tell the minimum number of operations required to make the weight of every edge on the path from A to B equal. In one operation, you can choose any edge of the tree and change its weight to any value. So this is similar to what I have already told you. This is pretty much similar thing. Queries are independent of each other, meaning the tree returns to its initial state on every new query. So this is to be noted. And the path from AI to BI, U to V, or say, is a sequence of distinct nodes starting from node AI and ending at node BI. So you have to return the answer. Let's have a look at the constraints. So the number of nodes uh, is of order 10 raised to power 4, and edges is of order n minus 1. These are the constraints given, and the weights are only 26 here. Number of different weights are 26 only. So at most 26 different value of weights will be there. Types of weights will be there. Input is generated such that the edges represent a valid tree. So queries are of length 2 into 10 raised to power 5. So queries length is of order 2 into 10 raised to power 4, not 5. Uh, and queries, each query is of length 2, which is A, I, and BI, or you can call it U and V. It's up to you only. So each value of this AI and BI lies between 0 to n. So you have to tell what is the minimum number of changes or operations are required in a between a path from AI to BI. Minimum number of changes. Minimum number of changes in weights of edges in the path from AI to BI. So if you see, let me clear this out. And this also. From root to this particular node and from root to this particular node, what is the lowest common ancestor they are having? This is this node. Lowest common ancestor, or say parent, lowest common ancestor. So this is the lowest common ancestor. And if I ask you, let me copy this one to the new slide. If I ask you, what is number of weights between and V? So you will say uh, number of weights between root to U plus number of weights between root to V minus twice of number of weights between root. Let's call this LCA. LCA. So this thing will be counted twice. X1 value. This will be counted twice. So you will be subtracting it, and these are nothing but number of weights. So this is pretty much the whole idea of the problem. Now, what we will be requiring to solve this problem, uh, prerequisites. First is uh, LCA of tree, doing binary lifting, Second is I think it is the only thing that you will be requiring. In the solution, there is not any other thing that I should mention, or you can say binary lifting as a topic itself. What this binary lifting thing is doing is the constants here, as uh, you can see 10 raised to power 4, n is of 10 raised to power 4. So generally, LCA is fine. LCA of two nodes are find out using in O of n time. And if let's say there are n nodes, and somehow we store these frequencies, which frequencies from let's say mm, frequency of u. It denotes uh, number of weights from roots to u. Let's say by running a DFS, we found this value. Depth first search in a single traversal we can store. Then the problem arises that you have to check for every, and the queries are of length 2 into 10 raised to power 10. So one loop will be running for each query. And for each query, you will be requiring this LCA. It will again require you of n times. M here is nothing but 2 into n. So overall time complexity will be of n square, which is 10 raised to power 8 operations. Your solution will be required. To implement what logic? This logic. This is the logic. Also, we can also mention that you should also know what LCA is. LCA of two nodes in tree. Using binary lifting, we can find this. We are here, and there is a limit of 10 raised to power 8 operations. Now it has become equal to the limit of the number of operations. Then you will get a TLE. So the number of operations should be lower than that. If you are not familiar with this concept, I will be providing a link describing how the time complexity of a separate solution works with time complexity of a separate solution varies with input size. So basically we have to optimize this approach, and only optimization we can be doing is this LCA of this binary tree. So what we will do is this thing will be running in O of log of n instead of O of n using binary lifting. So these concepts are a prerequisite Link of the videos for binary lifting video and LCA of a tree using binary lifting video will be provided. And for this LCA part, a link of article will be provided to you. Please go through this in order to understand the solution. So that overall time complexity will be order of n into log n. So the number of operations will be lesser than 10 raised to power 8 operations, and your solution will be getting accepted. So I will not be explaining you to the LCA and binary lifting part. It will already be covered in the videos and the articles. Videos, two videos plus one article. This you have to do. This is a prerequisite. If I go on explaining what binary lifting it, then the video will be very longer. So in order to keep the length of the video manageable, we are not including these two. I will be providing links anyhow. So I hope you have gone through that, and let's have a look at the solution. Basically, for each query, let me change the theme. Firstly, what you will do is you will make a graph representing the tree. Then this parent of array will store what is the immediate parent of a node. What do I mean by immediate parent of a node? Let's call this U, V, and Z. Immediate parent of will be V, and though Z is a parent of U, but it's not the immediate parent, just one above one level. So depth level will be the depth of the nodes. This is the, let's say, 0th level. This is the first level. This is the second level. This parent of matrix will be used in binary lifting. Now I hope you have gone through these two videos if of LCA and binary lifting. LCA and binary lifting. Also LCA by binary lifting. Why LCA is being required? Because we have to subtract this part. Which color should I use? I think it will be fine. For this part is will be counted twice. So in order to subtract this part, we should know what is the LCA of U and V. LCA of U comma V. It will be done using binary lifting in order to optimize the time complexity. Now this formula we will be applying for each query. This is for we forming the graph using the edges array. Using edges array. Weight frequency is from root to a particular node. What is the frequency of occurrence of a particular weight value? And then we will populate all these parent of depth level and weight frequency. Fill data in the parent of depth level and weight frequency arrays or say that. This is a simple DFS, depth first search, DFS of the graph that we have made using edges array. Once we are done with it, we will use binary lifting to process our queries. This is basically the same approach that I have been discussing with you. Result for a query between u let's say query is u v is number of weights in path between u and v minus frequency of maximum occurring weight in the path between u and v. So this will be nothing but the number of operations required. Number of operations required for each query. You will be answering that, and let's try to submit it. It is basically LCA using binary lifting. I have very well commented the solution for it, and once you are done watching the video and videos and going through that article, you will be able to understand it in a very much clear way. Let's try to submit it. As you can see, this is getting accepted. If you are still having any doubts in this, even after watching those videos and then coming to the solution and reading out all the comments, please feel free to ask the comment in the doubt section, comment section, so that I will be able to answer your doubts. So thanks for watching. Thank you.